Our speaker tonight is Grace Saba, an associate professor at the School of Environmental and Biological Sciences at Rutgers, who leads a team focused on biological oceanography and marine ecology at the Department of Marine and Coastal Sciences. Big mouthful. As New Jersey aims to get half of its energy needs from renewable resources in less than 10 years from now, a team of researchers at Rutgers Center for Ocean Observing Leadership, also known as RUCOOL, which is a really cool acronym, is playing an important role in developing and advancing the science that informs decision-making around one of those resources, which is offshore wind energy, which we have a lot of. Dr. Saba holds a Bachelor of Science degree in aquatic biology from the University of California at Santa Barbara and a PhD in marine science from the College of William and Mary at the Virginia Institute of Marine Science. She also did her postdoctoral research at Rutgers before coming on faculty. And she told me earlier that she's from Kansas, which makes a lot of sense why she would just love the ocean, because she didn't have one when she was growing up. So please join me. Oh, and let me just say one more thing. There will be time for questions after her talk. If you're at home, you can put them in the chat. And if you're here, Dr. Saba will be answering them. So let's get on with the program. Please join me in welcoming Grace Saba.
Hi, thank you so much, Sandy, for the introduction, and thank you, Melissa, for having me. I'm really happy to be here tonight, and hopefully you'll learn something about the research we're doing to help inform offshore wind off the coast of New Jersey. So I'm here representing a part of a team. So again, we're RUCOOL, Center for Ocean Observing Leadership. I'm one of 9 faculty in COOL, and we all have a very broad range of expertise. Physical oceanography, biological and chemical oceanography. We're also running a Masters of Operational Oceanography program that's meant to develop the workforce for the next generation. We have education outreach specialist, Janice McDonald, also on faculty. So it's quite a broad range of expertise in our group. And I'm here to represent all of us. So I'll be talking about projects that all of us are working on this topic. And we run an ocean observing system right through Rutgers University, and that includes things like satellites, so that we can look at ocean color, so how much phytoplankton, the small single-celled plants, are in the ocean. We can also look at things like sea surface temperature, so how warm or cold the ocean is at any given time. We have a CODAR network all along the East Coast, and that is allowing us to look at things like wind. So how much wind, what are the surface currents doing in the ocean? It's also it helps the Coast Guard search and rescue, so they know where to go in the event that they might need to search for someone. We also are deploying autonomous underwater vehicles called gliders. So this, if I have there it is. They look like little yellow robots that are flying through the ocean, and we have an array of sensors we can integrate into these gliders to help learn more about the ocean and different properties of the ocean without having to be on a ship. And then we integrate a lot of these data into models, so we can model the ocean and forecast what some of the conditions are going to be. So we do this with a lot of partners. They're all kind of listed below. But we really enjoy using a bunch of different technologies to observe the ocean. So the kind of emphasis and background that I'll need to talk about before I talk about offshore wind is what's happening in terms of climate change. So the Earth actually has a natural greenhouse effect where we have a nice balance of carbon dioxide in the atmosphere. That carbon dioxide is taken up through photosynthesis, so the plants are taking up carbon dioxide and producing oxygen. We have other organisms that respire carbon dioxide, so it's a nice balance of CO2 intake and output. And then the oceans exchange gases, including carbon dioxide, with the atmosphere. So it's typically balanced at the surface ocean. Oops, I keep hitting the wrong button here. Okay. What's happening is we have a lot of CO2 coming into the atmosphere through fossil fuel combustion, land use changes, so urbanization, removal of greenery. And that's creating, it's enhancing the greenhouse effect, so global temperatures are increasing. And the oceans absorb a lot of that carbon dioxide as well, and I'll talk about that in a minute. But let's talk about the impacts first to global temperature. So the carbon dioxide has been increasing quite rapidly in the recent years. This is carbon dioxide in the atmosphere measured at, through ice cores up until 1958, where we started measuring it at Station Mauna Loa in Hawaii. And you can see that there's been a pretty rapid increase of carbon dioxide in the past 50, 70 years. Due to a lot of that fossil fuel combustion and the rising use of the fossil fuel combustion. And what that is doing is that the ocean is absorbing a lot of that CO2, and it's increasing the heat content of the ocean. So this figure is showing the ocean heat content anomaly, where blue is cooler and red is warmer over time. And so you can see that kind of shift to warmer oceans over time, and so that's because 93% of the additional warming goes into the surface layer of the ocean. And so you're seeing that increase in ocean heat content. Now, it's not the same everywhere. There's places where it might be cooling a little bit, and then there's places where it might be warming more rapidly. And we are actually situated, where we're at in New Jersey, in an area where it's actually warming a lot more rapidly than other regions of the world. So that's shown right here. Again, ocean heat content. And that's likely, it's suggested that that's because of the changes in the Gulf Stream northern wall position. So the Gulf Stream is becoming a little bit farther north in our region. So we're getting warmer over time, and that warming is increasing pretty rapidly. This is just New Jersey's extreme temperature months, and so we're looking at just what are the warmest temperatures that we've seen throughout the years. And you can see a lot of high extreme temperatures that have occurred just in the past 4 to 5 years. So we're seeing a lot more extreme temperatures recently off the coast of New Jersey. So what happens? Why does it matter if the ocean is warming? One of the biggest impacts that we're seeing biologically is that organisms are moving. So they're moving their distributions. So this is showing average distance moved and going. You can see the lines going north on average, and this is on different locations. The northeast, where we're located, is this purple line. So you can see that northward shift of a lot of marine species over the course of several decades. Organisms are also moving into deeper water because it's cooler in deeper water. They're moving away from the shallower, more surface water where it's warmer. And so that basically the organisms can move then farther north and into deeper water. And we think of this typically in terms of the mobile species, so things like fishes and elasmobranchs like sharks that are moving. But we've also seen these distribution shifts in organisms that are less mobile, so the shell fisheries, so surf clams. And then it's projected that sea scallops and American lobsters will begin shifting their distributions over time in the next 20 to 30 years. So it's a pretty general trend that's occurring in the ocean and with respect to the marine organisms that are living in it. And then there's also a lot of other influences from that increased warming. So we're getting warmer temperatures, we're getting increased chances of drought, higher precipitation, less snow cover, and that snow cover is important because it actually acts, if there's a lot of snow on the ground, it's a light color that actually reflects light back up, and so it's called the albedo effect. And so it causes the Earth to absorb less heat. But when there's less snow cover, that kind of exacerbates the issue where the Earth is absorbing more heat. And then we're seeing also an increased intensity of tropical storms. So that's with the increases of 0.4 of plus 4 degrees Celsius. So those are projections, so this is today. If we're projected to increase over time at 4 degrees Celsius, we're seeing four times more drought, 30% increase in the intensity of storms. So that's where the concern is coming from with temperature. The other thing is that, how I mentioned before, the ocean is absorbing carbon dioxide, and what that does is that it creates what we call ocean acidification, whereby the ocean is absorbing carbon dioxide, and that decreases the pH of the ocean. And so since the beginning of the Industrial Revolution in the 1800s, atmospheric CO2 has increased by 40%. So this is, again, that kind of red line. But we're also seeing a drop in pH. So this is, we've measured pH off the coast of Hawaii since about 1988, and you can see that kind of simultaneous decrease in pH as that atmospheric and seawater pH is increasing. So since the Industrial Revolution, it's about a 28% increase in ocean acidity. And that's happening globally at a pretty consistent rate. But we also have these very dynamic coastal systems whereby local influences can act to either exacerbate ocean acidification or make it worse, or actually alleviate it. And so one of those things is fresh water coming in. We have a lot of fresh water coming into New Jersey from our bays and our rivers. And the fresh water is pretty naturally low in pH. These fresh waters also bring nutrients, and those nutrients can actually create phytoplankton blooms. So we like phytoplankton, right? They're the base of the food web in the ocean. They're those single-celled plants in the ocean that create a lot of oxygen that we breathe. But if we have too much of that and it's not eaten by other organisms, it creates a lot of material that sinks down into the bottom, and then bacteria will feed on that organic matter, and they will produce carbon dioxide, which then creates ocean acidification in bottom waters. So we have just very dynamic processes that are occurring in our coastal system that can influence the amount of ocean acidification in those local regions. Here's an example of kind of a seasonal profile where we have winter, spring, summer, fall, looking at pH off the coast of New Jersey. And we're measuring this using those autonomous underwater vehicles called gliders that I mentioned earlier. And these are looking at cross-shelf transects. So you can see in the winter time, so going from near shore to offshore, the water is pretty well mixed. It's very windy. The water moves and mixes from surface to the bottom. And so pH is pretty uniform. In spring, we start getting it gets warmer, so the water starts to stratify, meaning it starts to develop a two-layer system. And so by summertime, that two-layer system is completely formed, and the bottom water cannot mix with the surface anymore. And so what happens is you get a lot of those, like I mentioned before, the bacteria that are producing that carbon dioxide, and that creates that kind of acidification in the bottom waters in the summertime. And in the fall, we get a lot of storms. We have nor'easters. We have some hurricanes or tropical storms that may come through, and an increase in wind events that starts mixing the water column up again. So those are kind of the seasonal processes that we see across the region, but seasonally that can really impact the chemistry of the water. And we know that ocean acidification is increasing, so and is projected to continue to increase if we don't mitigate carbon dioxide emissions. So these are looking at different scenarios of carbon dioxide mitigation. So the red is essentially, this 8.5 is essentially if we don't do anything. So that's if we just continue as usual. So this is a business as usual scenario, and we don't do any mitigation. And then the extreme, the gray, is if we do a lot of mitigations, and then there's a lot of in-between scenarios. But if we don't do anything, or if we're doing, we don't do any more mitigation, that atmospheric carbon dioxide is going to continue to increase at a rapid rate, and then pH is going to decrease also at a pretty rapid rate globally. And this is the global image looking at the decrease in pH over time projected. So this is our concern, again, with with the increased carbon dioxide in the atmosphere. The ocean acidification impacts, just like temperature can impact organisms, and so this figure is looking at different processes that can be impacted in organisms from ocean acidification. So all the way from survival to growth to photosynthesis to metabolism. Anything below this dotted line means it has a negative impact from ocean acidification conditions. So we are concerned that, rapid rates of acidification over time might impact organismal physiology, as well as their reproduction, their behavior, swimming ability, and susceptibility to disease, because if an organism is dealing with something stressful, it has less energy to put into things like reproduction and dealing with another stressor. So those are the concerns there. So with that in mind, with what's happening in terms of climate change, this is the reason why governments are pushing for renewable energy. And one of those is offshore wind. And so, basically we're trying to create a different energy source as opposed to burning fossil fuels. And so that is the government's plan, is to try to put more emphasis into renewable energy to help mitigate climate change. So what is offshore wind? Offshore wind is a source of renewable energy. It's capturing the wind and then converting that to energy. Wind turbines are constructed in the ocean. Obviously for offshore wind. What that means is it doesn't occupy land resources, but it's being built in a very dynamic ocean, and that area is considerably larger than those on land. Right now, there's only 2 small operating offshore wind farms in the US. There's one off Block Island, Rhode Island, and it has 5 turbines at 30 megawatts. And coastal Virginia has about two turbines with 12 megawatts. So pretty small wind farms currently operating. But I'll show you in a minute, there's a lot more planned off the coast of New Jersey and along the East Coast. Offshore development faces many challenges beyond land-based wind, and that's really because it's being built in a dynamic ocean. We have seawater to contend with. We have organisms and that are moving in and out of the area, so we're concerned about that as well. So that is what offshore wind is, and these are the goals and the potential benefits in terms of the economy that has been reported in by the U.S. Department of Energy. So the federal goal is 30 gigawatts by 2030. So that's coming up pretty quick, and you can see the areas of potential development here. This is along the East Coast, but we're also seeing potential sites in Hawaii and off the West Coast. The states have established nearly 74,000 megawatts of offshore wind procurement targets to date. So that's basically the wind lease areas that are set off the states. It's predicted that it will trigger more than $12 billion per year in capital investment and create 83,000 new well-paying jobs by 2030. And there are more than 35,000 megawatts of offshore wind potential under development just on the East Coast alone. So why the East Coast? The East Coast is highly populated. It's one of the most densely populated areas in the United States. We have an intense power demand because of that high population density. You can see that in this figure at night, just showing all the lights on in those areas. But we also have a really strong wind resource. So we have a very broad continental shelf, so it's not rocky. It has softer sediments for development, and it's also a broad continental shelf, so it's not steep. It doesn't like drop off. So it's perfectly suitable for the development of turbines in that area. And also it has high wind, it's a strong wind resource, meaning that there's a lot of wind. We have a lot of wind in our area. So that makes this area pretty targeted in terms of the offshore wind development. So when we look at the states, and specifically at New Jersey, The goal for New Jersey by 2040 is 11,000 megawatts. And so these are the planned lease areas and the current lease areas at the moment. But again, we do not have turbines in these locations yet. So just kind of historically, where have we gotten our energy? We've gotten it traditionally from nuclear and natural gas, also coal, but that's been declining over the last decade. We've gotten a little bit of renewables up here, but this offshore wind goal is about half of what we've been using in terms of electricity. So we want to generate about half of our electricity from offshore wind, and so that's where it would be by 2040, according to New Jersey's goals. So going now into the research. So we've established that climate change is happening. We've established that offshore wind is coming to New Jersey, but it's complex because the ocean is complex where we are. There's a lot of different water masses coming in. There's freshwater inputs. There's a high seasonality in the area, and we need to know what that is. So we need to understand that variability. We need to understand that long-term change so that when that wind resource is developed in the region, we know if it is having real impacts on the ecology. So what is it like in the Mid-Atlantic Ocean? So this is a seasonal profile. I kind of showed you that when I showed you the seasonal kind of ocean acidification in the region, where the water is really well mixed in the late fall and the winter, and then we start creating that two-layer system in the early summer and through summer. And so that's a really warm water on top. And then below this is, we call this the Mid-Atlantic cold pool, which is essentially this cold water mass that gets trapped under this warm surface layer during the summertime. And it's very important ecologically for a lot of the organisms because they prefer cooler water. And this is going to be a video showing you what the cold pool does. So maybe if I can, is that not working? The videos don't work. Okay, that's fine. What I was going to just show was essentially the evolution of the cold pool through the season. So it will start in the late spring, early summer, and then it'll kind of grow and move northward, and it'll cover pretty much this area where my laser pointer is pointing throughout most of the summer. And then in the fall, once mixing starts, it dissipates. So, but that cold pool is really important because it's attuned to the organism, or the organisms are attuned to the cold pool in that it is a cue for their migration. So when during fall breakdown, when the cold pool dissipates, that's usually a cue for the fish, the migrating species, to start moving offshore. When it starts setting up in the spring, they start moving inshore. It's also a cue for spawning in the spring and fall for things like shellfish, so surf clams and sea scallops. And so it can be really important for recruitment and the abundance of organisms. So it's a very unique but very ecologically important feature in the Mid-Atlantic. So I've talked a lot about long-term climate change. I've talked about seasonal processes in the system, but we also have a lot of interannual variability from a lot of different forces. So things like large climate forcing, so these El Nino, La Nina, the El Nino Southern Oscillation, the Atlantic meridional circulation, oh my goodness. Azores, Bermuda High, the North Atlantic Oscillation. So there's these large climate cycles that happen at different cyclical times, so decades, multiple decades, 5 to 7 years, and they're all happening at different cycles. And so that can really impact interannual variability in the region. We also have, those can create changing wind and storm frequency and intensity. changes in precipitation, and then I've mentioned before changes in the Gulf Stream position. So where is that Gulf Stream? If it's farther north, where it's typically warmer in the region. So that can change year to year as well. So just in general, very dynamic region, a lot of interannual variability and seasonal variability. So this kind of summarizes that, and this is why we need more information now before these wind platforms are put in. So the New Jersey coastal shelf system is highly variable and complex, and the organisms are tightly coupled to those changes. So ocean conditions can create changes in organism distributions, and that happens on seasonal and annual scales. And then again, we're situated in an area where it's warming rapidly, and we have other things like ocean acidification that are happening, and so we're susceptible to that long-term change as well. And so we need to establish that baseline from which to assess impacts from offshore wind development, right? Because if we don't understand what's happening now and the variability that is occurring in the region, it's very difficult to assess if the offshore wind will have impacts once the wind farms are operating. So that is what we're trying to do in terms of the research. So some of the concerns and research priorities for this region are, well, some of the concerns are access. So particularly for the fishing activities, so the commercial fishers are concerned that they're going to be displaced from the wind farms. So that is a concern that needs to be addressed. There's also ecosystem impacts. So the influences on physical and biological processes once the wind farms are in and operating. So those are things like how wind turbines might affect water column stratification. So what that means is, will there be turbulence or changes in mixing dynamics that occur when the wind farms are in that might change that two-layer system or cause mixing in that two-layer system? And then what are the impacts of that? And then one of the major ones ecologically is if the presence of the wind farms in general will impact things like distribution behavior, reproduction and survival of marine fishery resources. And then navigation and safety is another concern, particularly again for the fishing industry while they're fishing or while they're transiting between fishing locations. So what are we doing in terms of research? So these are the four kind of major things that I'm going to cover today. There are a lot more projects, and they're all kind of summarized on this website down on the bottom right. So feel free to check that out. But I'm going to just briefly describe four of these projects tonight. And the first one is establishing an oceanographic and ecological baseline. And for this, we're using those gliders that I talked about before, and they're providing data that to try to determine mechanistic linkages between physics and biology. If we can get a better idea of what ocean physical conditions are creating certain biological processes, or for instance, the distribution of certain species, then we can better project where they're going to be in the future, but also it'll help us figure out if offshore wind is going to create impacts. And then I'll cover these three right after that, and I'll go through those again when we get to that point. So I'll start with the gliders. So traditionally we use, there's a lot of different platforms that we can use to study the ocean. There are satellites that I had mentioned before to look at things like sea surface temperature and the biomass of phytoplankton in the ocean globally. We can use moorings or buoys that have different kinds of sensors on them. And these are really good. These are moored typically in one location. And these are really good for if you want a long time series of data in one location. So it won't give you a good spatial resolution, but it'll give you really good resolution over time. And vessels are really good in terms of you can go on a boat, you can actually collect organisms out of the water. So you can get fish, you can get squid, you can get zooplankton. So you can pull things out of the water and actually count and identify them. So it's really beneficial for that type of observations. But ships are costly, they're very expensive, and they use a lot of fuel. And so you can typically only go out for a little bit of time. So you can cover some spatial area, but not for very long because they're cost prohibitive. So our group uses gliders a lot. This video probably won't work. Yeah. Oh, maybe it's because I have the laser pointer on. That might be it. Let me. Oh, there we go. All right, so these are underwater gliders, and they are buoyancy controlled, which means they don't have a motor or a propeller on them. They're controlled basically by weight. And so what you just saw was water being taken in to the front that makes it heavier in the front, and then it dives, and it has wings for forward motion. And then it has an altimeter, so it'll dive down, and it has an altimeter to basically detect the bottom. And once it detects the bottom, then it'll push the water out of the nose. It'll move a battery pack back and make it lighter again in the front. So it dives in these sawtooth patterns through the ocean. I know the camera can't see me, I'm going like this. It dives in the sawtooth patterns, and so it collects data, pretty much every 2 seconds. So we're getting really high resolution data collection, and you're getting that from surface to the bottom. And then it has an Iridium and GPS system in the back. So when it surfaces every now and then, it can transmit that data back to our lab. And so we can sit at a computer and see the data in real time, which is great. But it allows you to kind of adapt your sampling. If you see an interesting feature, you can go back or stay in that area. And then you can communicate with the glider as well, so you can change its path every time it surfaces as well. So they're just really unique systems and really good to work with. Oop. All right, and so we like them because it does provide that high resolution sampling, so you're getting really nice data throughout the water column, and it's covering space too, so it can go about 20 kilometers per day, so you're getting nice spatial resolution as well. They're cost effective, so they're cheaper than going out on a boat for several days. They can stay out in the water for 3 to 4 weeks in our coastal ocean, so it covers a lot of time as well. You can recharge a battery and put it right back in also. It can go out in hazardous conditions. We have a whole hurricane program where they're putting the gliders out in the middle of hurricanes to help with studying how the ocean acts during a hurricane. It's also helping with getting better understanding our hurricane intensity forecasts, or improving them, because we're providing ocean data to the atmospheric models for hurricane intensity forecasts. And then we can augment vessel-based surveys, again, because we can put these out when the boats can't go out. And we're hoping that we can navigate wind farms because they're small. They're about 1 meter long from front to back. So they're pretty small, but there are constraints to flying. Once they're down under the water, you can't communicate with them, so they can't change their path. So there's some challenges there in terms of trying to navigate through a row of turbines, for instance, if we had to do that. But they're really great because they can house a bunch of different sensors. So the physical sensors, so temperature and salinity, chemical, so dissolved oxygen, pH, biology, so all the way from phytoplankton to fishes to zooplankton, through active acoustics. And then we have listening devices called passive acoustics for detecting marine mammals. And we also have passive acoustics, so telemetry. So if fish are tagged, so if scientists tag fish in the region, there's a receiver on the glider that can listen for the tags, and so that'll give you an idea of where the fish is. It tells you where a fish has been located. So it gives you information on fish movement and migration. And so one of the studies that we're doing right now it's funded by the New Jersey Offshore Wind Research and Monitoring Initiative. So that's the Board of Public Utilities and New Jersey Department of Environmental Protection. And we're flying gliders seasonally and sometimes in between seasons to get better temporal coverage, but with a full complement of sensors to capture that oceanography and the ecology of the system. And so these are the types of data we're collecting. So these are our flight paths. So this was this past spring, summer, early and late fall. You can see these are the profiles of the gliders, so looking from surface to deeper water along the glider path. So we can look at things like temperature, salinity, which is not shown here, chlorophyll, again, that's a proxy for the biomass of phytoplankton in the water, dissolved oxygen, pH, and then here is showing aragonite saturation state, or omega, which is another parameter for ocean acidification. But what's really great is that we're able to characterize the variability of the system. So on a greater than seasonal resolution, we're relating those physical, chemical, and biological variables together. We're also contributing data that's relevant to ongoing environmental and ecological change. So we're contributing to those kind of historical data sets and adding more high resolution data to those. We've also observed some multi-stressor events, which means that when the water is affected by more than one stressor. So in this case, we had low dissolved oxygen and low pH occurring around the same time during this past summer. And then during that time, we also had reported fish, lobster, and crab mortalities in the region that may have been linked to that multi-stressor event. A lot of these organisms some were in pots, like crab pots or something, but some were just not in pots and just laying on the bottom of the ocean that were reported typically by fishermen. And so, you know, it was good to capture the data to see if maybe that could have explained the fish mortalities in the region. That event persisted throughout the summer, but then finally was alleviated once we had the storms mixing the water, and so the bottom water became oxygenated again and had a higher pH after the storms went through. And then we're also co-locating the physics with the biology. So these are looking at zooplankton and whale distributions in these plots. Here's the glider path. These are flying through different lease areas. We have the bubbles are depth integrated zooplankton biomass. So in this case, it's typically fish prey or baleen whale prey, so the North Atlantic right whale prey. And then this is for spring and fall. And then on the right, you can see that's the vertical profile showing the depth distributions of zooplankton, which again are very prominent prey items for fish and some of the whales. And so we can start to get a sense of maybe where some of these prey hotspots are, and then why are they there physically. So we're starting to look at those mechanistic drivers, and where are they in location to their predators, so things like whales. So the North Atlantic right whale here is the detected in these two areas where there's red dots. All right, so talking about the North Atlantic right whale, they migrate through our region, so it is important to understand their ecology and their movements throughout our region. There is concern about the impact of offshore wind on marine mammals, as I'm sure many of you have heard. But they do go through our region typically in the springtime, and then in the late winter they'll come back through. They're going up to their primary feeding grounds up here in the Gulf of Maine. So they do move through our region. So again, it's important to know where they're at. They are highly endangered species. And so we do have some projects that are looking specifically at that. Here's one by my colleague Josh Kohut, who had a glider out with the listening device to detect whales. The red is where the North Atlantic right whale was heard or detected. And so what he's doing is looking at the physics and how the physics might determine why the whales are located where they're at. So he's specifically looking at things like frontal systems, so where different water masses meet. It creates a front where a lot of things aggregate, and that includes plankton, which are prey items for the North Atlantic right whale. And this is one front, and you can see right along this one front is where we detected the two North Atlantic right whales. So we're starting to really look at these data and try to figure out if these physical features are concentrating prey and then attracting their predators. So that's one thing we're doing with these gliders. So just to summarize, the glider study is, these glider-based studies are providing that seasonal or higher than seasonal resolved view of regional ocean ecological conditions. And that's all the way from the physics, the chemistry, and biology, from phytoplankton to marine mammals. So we have ongoing projects that are looking more into assessing those relationships that I talked about before in terms of the mechanistic drivers of where these organisms are and why they're there. So going into the cold pool dynamics, am I okay on time? Okay. Going into the cold pool dynamics, so again, that cold pool is that cold water mass that sits below that warm surface layer from late spring to fall. And what a few of our faculty in our group are looking at is what could be the potential impacts from offshore wind on cold pool dynamics, and then just figuring out what the research needs are so that we make sure we're out there monitoring what we think what could happen in terms of the offshore wind development. So this was led by Travis Miles in our group, but also Josh Kohut, Daphne Monroe, and several graduate students at the time. And some of them are still here, and some of them have graduated. But what they really did was they conducted a review to kind of figure out what potential interactions might be between offshore wind farms and this cold pool feature. The specific research needs and questions that came out of that were primarily these three. So how much overlap is there between where these offshore wind energy lease areas are going to be and the cold pool? So that was just the kind of the primary question was, is there overlap? And that will mean how much we intensely study the dynamics. What is the threshold of stratification? So again, the stratification is that two-layer system. What is the threshold that will be impacted by offshore wind turbines? And then how does this relate to the seasonal evolution of the cold pool off the coast? So those were the three kind of primary questions. The understanding is that we have the wind turbines in the ocean. They're harvesting the wind, but the turbines themselves might create some sort of small-scale turbulence that then will that impact this two-layer system, right? So here's your warm surface layer, here's your cold bottom layer, the cold pool, and then you have this, transition in the middle. We call that the thermocline. And if there's turbulence there, what does it do? Does it increase mixing of these two layers? We really don't know the answer, but that's why it is a research need to figure that out. They did conduct the study and publish this study about the overlaps of the cold pool and the offshore wind lease areas. And here you can see it's a seasonal study looking at that. So the highest overlaps were in spring and late spring through summer, where the maximum overlap was about 81% of the cold pool and the wind lease areas. So that study was conducted, and there's going to be more work done, modeling work done to try to tease out what the potential impacts on the turbulence effect might be. And then we have a large group of faculty, both at Rutgers and our collaborators at Monmouth University, that are working towards developing and executing fisheries monitoring plans in individual wind lease areas. So these are actually required by each individual wind developer. They have to have a fisheries monitoring plan whereby they collect baseline data, they're collecting data during development, so while the wind farms are being developed, and then they're collecting data after to look at impacts. So it's a kind of a before-after impact study, and we can measure all sorts of different things. And so the kinds of things that we're measuring are, conducting these different methods. So benthic trawl survey, and that's to quantify the abundance, distribution, assemblage of benthic or soft bottom and forage fishes. A structured bottom survey, so that's looking at structure-associated fishes, so black sea bass, which the hypothesis there is that they might actually increase in abundance with offshore wind farms because they're going to be providing more structure in the ocean. There's a clam survey, so we want to know if the abundance distribution of clams and age of clams will be impacted. Pelagic fish, so looking at fish that are living in the water column that aren't typically collected by things like a bottom trawl survey. We have a telemetry component, so we're tagging fish. We have acoustic receivers out to look at, again, their movements and migrations. Are their migrations changing because there's a wind farm there? So those are kind of the primary questions there. We also have an eDNA and an oceanographic survey. So the eDNA is actually, you collect a water sample, you collect its DNA, and then you can kind of get a sense of the species composition that's been in that parcel of water in the most recent time. So it gives you a good idea of biodiversity. And then we have oceanography. Again, I've described that a lot already, to collect that physical, chemical, and biological environment to inform the fish. So again, kind of linking those physical conditions to the biology. And these are, again, multi-year initiatives to encompass before, during, and after construction. And then lastly, I'll talk about effects on and mitigation for fisheries. So in this case, it's the focus primarily on the Atlantic surf clam. And this work is done being led by Daphne Monroe, and I'll talk about that. I'll introduce her on a different slide. But first, why do we care? We care because offshore wind projects are going to be occupying fishing habitat. And that is a real concern for the fishing industry. And what we've seen globally is that fisheries, there are conflicts, there are overlaps with fisheries and offshore wind, and it seems to be that the bottom tending gear is at greatest risk. So gear that has, like, dredging for surf clams, so things that are living on the bottom, that seems to be what's going to be at the greatest risk because of the because you're going to have cables. So you're not just going to have the turbine there, you're going to have the cables that are going to bring the power back to land. And so dredging and pulling up sediment while you're dredging is going to be challenging in those areas. So Daphne Monroe showed here, and Sarah Borsetti here did a kind of a two-part study where they're trying to figure out how the Atlantic surf clam fishery might be impacted by offshore wind. And I'll show you just some of those results in a minute. But first, what is the economic importance of shell fisheries? If we look at weight, Menhaden is of the most biomass in the region for commercial landings. But if we look at commercial value, so the economic value, it's mostly these invertebrates, these shellfish, these molluscan shellfish. So surf clam, ocean quahog, and sea scallops probably make up most of the economic value in the state of New Jersey. So commercially, they are extremely important, and so it is a real concern if fisheries for those species are impacted. So Daphne's questions are primarily, what are the economic and management consequences of fleet displacement? So if the fishing fleet, if they have to be displaced out of these wind farms, what does that cost them and the New Jersey economy? What are the surf clam populations within the wind leases? We need to know that, right, to understand the impacts after they're put in and operating, and how might overlap among fishing grounds and offshore wind change over the wind project lifetime. So I'm going to talk about these. This one is, Daphne is working on this, so she's really trying to incorporate not only the offshore wind impacts over time, but also climate change. So it's a very complex question that she's aiming to answer. But some of the results here for the economic impacts, the highlights here are that when she did the analysis for increasing restrictions to the fishery over time, is that the number of trips decline and average time at sea increases. So they're not able to go out as often, but they stay out for longer. And that might decrease fishing. The decreases in fishing activity cause reduced revenues between 3 and 15%. So it can be pretty significant, is projected. And that this displacement increases the fuel costs because they're having to stay out longer to maneuver around these wind farms. And the fleet in Atlantic City is disproportionately impacted, primarily because of the location where they typically fish is higher area in these wind lease areas. And so the other thing Daphne is trying to do is mitigate for that, right? So maybe if we change the gear a little bit, it makes it a little bit more easy to maneuver in and out of a wind farm for a surf clam dredge. And so she has two objectives here. The first one is to construct a scientific surf clam dredge that has smaller bar spacing, but that allows it to be smaller, which is good. In terms of, you can do shorter tows or shorter trawls, but you still want it to collect the same amount or the same size classes of clams. But if we have shorter tows and it's smaller, then it can be you can more easily maneuver around or inside of the turbines. And she's also so that has been done. They've constructed that. They've been testing it out and doing these calibrations with the new dredge. But essentially what they want to do is look at how efficient it is at collecting the clams, because you want it to have the same efficiency and the same size selectivity, because you want to be able to compare that to historical surveys like the federal survey. So here's just a picture of the dredge. So this one is the traditional one, and this one's the modified dredge. So you can see it's narrower with smaller bar spacing. I think I pretty much said all this already. But here's the stations that she occupied. Again, going over the same federal surf clam survey stations to do the calibration experiments. And here's just an example of the size range of surf clams that were collected in that experiment. So, she's really working to try to mitigate the impact on the surf clam fishery to be prepared for when the turbines go in. And I'll end with this. So this is, so I just went over essentially 4 projects that are going on between our collective team. But we're just a small part of what's happening at Rutgers in terms of offshore wind. There's this offshore wind energy collaborative at Rutgers, which includes over 70 faculty from the different campuses at Rutgers. But the goal is to establish Rutgers as a national leader in offshore wind innovation, but to really promote the research to help inform the development of wind. But kind of the day-to-day things that we're doing are convening, networking, speaking with stakeholders, developing curriculum, and then conducting the research and monitoring as well. So I'll end there and hopefully okay on time. Thank you.